Okay, YouTube, in this video, we're really going to explore really the meat and potatoes behind all of this exponential growth and decay modeling and logistic growth modeling and logarithmic growth modeling. Basically, we want to model data sets using really good models that fit data. And so what I'm just going to kind of direct your attention to is all of these data spreads down here. If we were to be running an experiment, and who's to say what our variables x and y are, but basically, if you were to see this pattern of data, you'd be like, oh my goodness, or at least hopefully you could say that, for something like this, maybe we could fit a logarithmic curve to this data really well, so well that we could make predictions with this data, or maybe kind of generalize natural phenomena, or just seeing how people behave. You could see this graphically. So we could see that we have different types of models, and I want to kind of point them out here. The first two being exponential, and we could see that, and I'm just kind of drawing a line through this here. We could see that an exponential growth model would be something that would look similar to this. And so for any data that looked like that, or potentially like something like this, what we could hope to do is fit a curve along this data to kind of help us make predictions. And likewise, these two that you see here, we only have data, say, for positive, say, x values. Let's put it that way. But for just a part of, say, like a logarithmic curve, we can see that this would look maybe like a logarithmic curve, or maybe a reflected logarithmic curve that starts to grow really slowly to the right there. And then for the last two here, we say that these are both linear models, and basically because they follow a line. There would be some line that would fit this data extremely well. And so our job in this video is just kind of explore how we could use a model to model specific data, and how to determine which model would be appropriate, exponential, logarithmic, or linear. So let's take a look at an example here. In example 4, it says choosing a model for data. It says the data in table 4.6, that's this table over here, indicate that between the ages of 1 and 11, the human brain does not grow linearly or steadily. So we see that a scatter plot for the data is shown here in this 4.25 example. So basically what you see is this, the age from 1 to 11, and it looks like they don't go through all of the ages here. But we certainly see the percentage of adult brain size that you've obtained at that age. And you can see that it grows really rapidly at first, but then kind of slows down as they get towards 11 here. And that scatter plot, this is basically just an XY plot of this very same data that you see over here in this non-XY table. And so what we see here is this: we say, what type of function would be a good choice for modeling this data? Well, now going back and looking at our guides here, I would say, well, this looks kind of like it grows rapidly at first and then slows down. This would be a logarithmic model. And so what I want to point out here is, you see on top of this logarithmic model, it says a plus b ln of x. Let me tell you this, we are going to constantly be after these values of a and b, and we can use a calculator to obtain them. So for right now, just know that there are some a and b that when we write them in here, right into this model, it looks just a lot like this data. Okay, it's the best possible model. So for right now, what we're going to say is that I think that this right here looks like it could be a logarithmic model. And so I would say I think a log model fits the best, fits best. And I'm going to write what that log model is. We say it's y equals a plus b ln x. Okay, and so here's our logarithmic model right there. So with respect to actually determining this on our own, well, I've got a couple of examples here. We'll take a look at them, but it says, how about just checkpoint 4? Let's read through this. It says, table 4.7 over here shows the populations of various cities in thousands and the average walking speed in feet per second of a person living in that city. That's kind of an interesting set of data to correlate. But it says create a scatter plot for the data. Based on the scatter plot, what type of function would be a good choice for modeling the data? So what I always suggest is looking at the span of x and the span of y. We would say that I'm going to allow this to be my x data and this to be my y data. But let's go ahead and label this out here. We say that as the population grows, we want to see the relationship between it and the walking speed, and this is in feet per second. I really want to see this here. So in terms of our very smallest and largest x values, our smallest is 5.5, our largest is 342. I think we need to go past 342. So how about this? I mean, we've got a lot of room here. We can see that there are some major notch marks every 5 notch marks. And so 352, suppose I have 6 major notch marks here. If I were to go by, say, tens, then this would get me to 300. So maybe I need to go by 20s, and if we go by 20s, that would put this at 100, this would put this at 200, this would be 300, 400, and 500, and so on and so forth. You want to choose an appropriate scale. So with respect to our walking speed, we see that we have, basically 0.6 is not very significant, up to 2.2. So I'm going to go by tenths, as a matter of fact. And what this means is I can say 1, 2, 3, 4, 5. So this would be 5/10. 1, 2, 3, 4, 5. This would be 1.0. 1, 2, 3, 4, 5. I don't know if I'll be able to fit here. I'm gonna try to make this work. 1, 2, 3, 4, 5. So I kind of underestimated. This is 2.0, so 2.2 would be way up here. Sorry about that, everybody. But basically, what you're going to see is this: 5.5 thousand, which is just barely away from the y-axis here. We're at a height of 0.6, and so in a different color here, we can see that right here would be this point. 14 wouldn't be much further, but that would be at a height of 1. So a height of 1 would be like maybe right here. It would still be really, really, really close, I suppose. Actually, this 5. Yeah, okay, we're good. So that was it, 0.6. I suppose at 14, if we're going by 20s, 14 would still be within here. I guess that would be a good place to put it. So 71, comma 1.6. 71 would be 60s here. Here's 80. 70 would be in between, and we're going to go up to 1.6 here. So 1.6 would be about right here, 1.6. And then we'd say, okay, so 138. 138, here's 150 right down the middle of the road. So here's 140. 130 would be right before this. 138 would track up to 1.9, which is way up here, almost 2. And so we would say that the last one here, 342. 342 would be 340 is about right here. And so it'd be at 2.2. And so we could see that this right here, if we were to say model this data with a curve, I could see that it flattened out. And so this looks like a logarithmic model would be the best possible model for this data set here. Okay, so basically what we want to do is find a model that's going to fit this very, very well, and then list the model that we're going to use here. I suppose that we would write that this is y equals a plus b ln of x. Cheers.